Before we get into what Schlumberger specifically is doing with Google Cloud, I'd like to give you all an introduction into high-performance computing and Google Cloud, what our philosophy is, how we look at implementing HPC in the cloud. So much like Google's overall philosophy, our mission statement for high-performance computing is to democratize HPC and make it universally accessible and useful. Right, so this is a big, lofty goal. What do we actually mean by this? Well, and sort of what's driving this is what I want to get into during this discussion. What's driving this is basically, it should be no surprise to anybody, a massive need for computing in the marketplace, right? So this is a graph of the top 500 supercomputers, and you can see that in total we've exceeded an exaflop now, and we're soon expecting to see exascale systems out in the wild ready to use, right? And it's not just compute that's growing, and it's not just these top 500 supercomputers that are sort of leading this charge. This is across the industry. So in terms of data, we see that data has had a massive explosion just in the last 10 years. Los Alamos set up their Roadrunner system in 2008 that had 3 petabytes of high-performance storage on it, built by Panasys. And at that time, that was an incredible amount of storage, and it was incredibly fast, 55 gigabytes per second of throughput, right? 10 years later, in 2018, the recently built Summit system at Oak Ridge National Lab is at over 250 petabytes and over 2.5 terabytes per second, depending on what time of year you ask, of throughput, right? Which is pretty incredible. So a massive explosion. So how does this relate to what our philosophy is? What we really want to do is we want to let you build these sorts of class of systems yourself, right? So, for example, we partnered with a company that you may know, DDN, Data Direct Networks, which is a storage provider, and you can come and talk to them here at their booth. And we actually built a marketplace solution, which is basically our click-to-deploy solution for DDN to build a Lustre parallel file system on Google Cloud. And just to test it out, we built the number 8 file system, storage system on the planet, arguably, and placed number 8 on the IO 500 list, right? Just to test it out. So you'll be able to very soon get your hands on the same code, the same building blocks that were used to build this system, and build one just like it for yourself, right? That's the sort of software work that we're doing to democratize HPC. In terms of what customers have done, University of South Carolina has a principal investigator actually in the room today who is doing microbiome research and using microbiomes to study climate change. And so they had a large data set that they needed to compute, and they realized that if they had commandeered the entire university's cluster, right, taken it over entirely just to themselves for months, they would have been computing that data set. And if they had waited in the queue, it would have been years, right, of waiting to get access to the compute power that they needed. So what did they do? They came to Google Cloud, and we were able to do all of that computation in 16 hours using 125,000 cores, right? He built an auto-scaling Slurm cluster using a simple set of scripts that we have open sourced on SkedMD's GitHub for Slurm to build a very simple auto-scaling cluster. Started off with 0 compute nodes, submitted a job, and it scaled to 4,000 nodes and then back down, right? So this is the type of power that we want to put in users' hands. So how are we doing this? We have 3 main pillars. In terms of infrastructure, something you always need, right? We're building a high-performance infrastructure specifically for HPC. In terms of software, we're open sourcing, building, and partnering with a lot of open source vendors and other software vendors to provide the most popular software packages available today. And we're also partnering very closely with the community and with organizations within the community to make it easier for HPC researchers to get into the cloud. So in terms of infrastructure, very quickly, 3 things that you really need for HPC infrastructure. Oh, excuse me. Compute, storage, and networking, right? So in terms of compute, everything that you would compute on Google Cloud, whether that's in Kubernetes Engine, BigQuery, or otherwise, is run on Compute Engine, right? This is our infrastructure as a service. It's highly configurable, so you actually can customize your instances. You don't have to fit within our preset set of instance profiles. You can use a slider, as you can see in the bottom right, to set the number of cores and the amount of RAM you need to exactly match the HPC problem that you're trying to solve on that machine, right? So you don't have to overspend and waste cycles, waste cores You can tune the system to be exactly what you need. We support up to 160 cores per instance, up to almost 4 terabytes of RAM, and we have up to 7 terabytes of Optane storage per instance, right? Of course, we support GPUs, so you can attach up to 8 NVIDIA GPUs per instance. We have them attached by PCIe X16, so you get the fastest possible performance on that instance and on those GPUs. We have NVLink between the GPUs, and we have a wide variety of families of GPU processors that you can use today, including the new T4s. You might have noticed preemptible VMs. These are a handy thing that are really essential to most HPC today. And this is actually one of the things that University of South Carolina made heavy use of. These are up to 80% off of an identical standard instance, so you can use the same customizable instances, attach GPUs to any of those instances that you like the same way you can normal instances, except that they live for a maximum of 24 hours and can be preempted anytime within that 24 hours with 30 seconds of notice. So there's a flat fixed price. You don't have to bid. You don't have to wait for these instances, but they work a little bit differently, right? They live for 24 hours at max. So these are really, really good for checkpointed HPC codes, for high throughput computing codes where you can restart an individual process without impacting the rest of the job. And we see a lot of success in those areas because of the cost savings, even though you might get preempted for some percentage of that computation time, that wall time, right? You might lose that. It still comes out on top. So what is an example of what's been rendered and done on GPUs in Google Cloud? Well, Jungle Book is a great example. Disney and MPC, which is a rendering firm, used 5.5 million core hours to complete almost 1.5 million tasks, rendering tasks to build the Jungle Book movie entirely on Google Cloud. In terms of storage, we have a lot of options for storage, but just to focus on a few quickly, Google Cloud Storage is our exascale object storage. So this is the system that's really good for dumping a lot of data in that you plan to process later, possibly processing it right directly off of Google Cloud Storage using things like GCS Fuse, which is a Fuse plugin for Google Cloud Storage that makes Google Cloud Storage bucket look like a local mount. Very easy to get started with a POSIX file, with a POSIX mount that way. Local storage is very good for scratch storage. This is our NVMe SSD, physically attached and very fast. And then we have a number of partner solutions and hybrid solutions, like I mentioned with DDN, as well as others that you meet here, like NetApp and Elastifile. And then in terms of networking, we have a massive global network. We've actually invested billions of dollars in our network just in the last few years. We have hundreds of points of presence where you can get into the Google network, and this will come in handy in a second, as I'll explain. But it's really a massive network. And when you have hundreds of points of presence and undersea cables that you manage yourself, you look at a network a little bit differently, right? You look at building a network as laying undersea cables and avoiding shark attacks on those cables. Because for some reason, sharks really like electromagnetic signals that are let out by these undersea cables, right? So there's a lot of things that go into building a network like this that you might not expect. But all of this infrastructure really goes into something. So if you look at the bisectional bandwidth of the internet, it's about 200 terabits a second. If you looked at the bisectional bandwidth of just one Google data center internally, it's over a petabit of bisectional bandwidth per second, right? It's actually closer to 1,300 terabits, but I can't find a legitimate source for that I can share with you. So petabit it is, right? So when you have such fast networks, when you have shark-proof networks, you really want to make sure people are taking advantage of it, right? So where a typical cloud provider, or basically anything on the internet, lets you ride the internet as long as possible before you get into their network, we take the opposite approach. We want you on our super fast network. We want you to be protected from sharks. So we get you into our closest point of presence to you as fast as possible so that you're riding our backbone network as long as possible rather than jumping around through the internet. Right? We use something called cold potato routing rather than hot potato routing, which means we decide on the lowest latency route for you before we start routing you, right? And that leads to a lot of advantages at scale. In terms of the individual instances, we support up to 15,000 virtual machines per virtual private cloud network. So that's a lot. If anybody needs more than that, please let me know. I will help. We have very predictable low latency. It's around Ethernet speeds. And then our bandwidth scales linearly at 2 gigabits per second per vCPU. So it's very easy to understand what kind of networking you're looking at, right? That goes up to 16 gigabits per second per VM today, but that is likely to be increased shortly. And you can see every time we release a new version of our software-defined network, our latency improves. Last time it was about 40% improvement of our latency, right? So you can be guaranteed that it will continue to improve. And we're working on tailoring a lot of latency-sensitive codes like MPI and others to work very well for our network. In terms of software, Google has a long, long history of improving and writing white papers and open sourcing computer science, basic fundamental computer science. And that started back when we started with MapReduce, right? We authored the MapReduce white paper, which started this big data revolution. And it continues today in things like the genomics API, which lets you very simply run an entire genomics pipeline. And that's actually what the Broad used to get their genomics processing down to $5 a genome. All the way through Slurm on GCP, through machine learning with TensorFlow, and even quantum computing with Cirq, our quantum computing open source framework. But it's not just our own internal work, it's also the work that we do with partners, whether that's with vendors like DDN and NetApp, who are very popular and solidly entrenched in the market, or whether that's with groups like Slurm and others like Broad and Firecloud and HT Condor to open source that code and make it available for free to users so that they can customize it, use it, and not have to pay for it. So then, just in terms of community support, what are we doing to assist the community in general, as well as in onboarding for HPC? Well, we look at the community as everyone, right? So in the global community, first of all, we're very focused on green computing. So this is one of our solar farms in Chile. It's actually generating 80 megawatts, and that's entirely going to Google Cloud. So all of the computing that we do is 100% renewable, and it has been for the last 11 years and counting, over 11 years, right? We have purchased and generated 3 gigawatts, not gigawatts, of renewable power, and that power is all of our data centers, right? So it is possible to do high-performance computing in a environmentally conscious way. But it's not just the global community, obviously. There are much smaller communities. So we support events in a very strong way, whether that's through hackathons, external events, or our own HPC days, which we have one coming up tomorrow in Sunnyvale, actually. These are opportunities to get hands-on in Google Cloud. And if anybody has an event that they think we would be interested in sponsoring, definitely let us know. But we also have research credit programs for scientists who are doing advanced computing on Google Cloud, and also faculty grants for faculty who are teaching students on Google Cloud. And we also partner very closely with a number of groups, but one of the most interesting is the National Science Foundation, where we've started just this year a number of programs to make it much, much easier for grant-funded researchers and scientists to get access to the cloud and start using it very easily. So with that, I will pass it off to Abhishek, who will tell you about how Schlumberger is solving their toughest problems on Google Cloud.
Okay, so thank you, Wyatt. So Wyatt told you guys about the great capabilities that Google Cloud has and the different types of GPUs that are there. Is the mic functional? Okay, okay. So I'm going to talk about how Schlumberger has been using some of those great capabilities, and in particularly how we are using some of the different types of GPUs that are there. So about myself, so my name is Abhishek Gupta. I lead the high-performance computing and 3D visualization. Here in Menlo Park, we have a software technology innovation center where we look at the latest computer science technologies and see how we can apply in the oil field domain. So some of the work that I'm presenting today has been contributed by the innovation team, the people listed here. And besides the innovation team, then there have been teams involved who have taken the work, the innovation that has been done at this Software Technology Innovation Center here, and commercialize that through our software technology centers. And of course, our partners, especially in particular in this case, Google and NVIDIA. Without them, the work that I'm showing wouldn't have been possible. So how many of you here are actually, to some level, know about the company Schlumberger? You can raise your hands. Okay, so little more than 50%, I would say, already know about Schlumberger. I'm going to give you a brief introduction about what Schlumberger is. So Schlumberger is an oil field services company. Our customers are essentially oil companies like Chevrons and Exxons and others. We provide technology for oil companies. We provide services. And specifically focusing into software, we provide software solutions which helps oil companies. So Schlumberger has been in the business of measuring the subsurface. So one of the things that we do is the first stage of, if you think in terms of the oil industry, the first stage would be to discover where the oil is. So oil discovery, discovery of reservoirs, and that happens through this subsurface modeling process, right? So this has been working well for Schlumberger. We are the leading supplier of technology, project management, and information solution to oil and gas industry. So to look into more computer scientist perspective in terms of the type and the volume of oil field data that we generate. So you can see some of our different types of oil field data. So seismic data, which I'm going to focus on this talk today. So if you see onshore seismic data, which is the land oil fields. So each of the survey, for instance, here can generate up to 6 to 10 terabytes per day. And then the survey can last 6 to 12 months. And you can have tens of projects per year. Similarly, if I talk in terms of the marine oil fields, these can be petabytes, so 5 to 10 petabytes of data per project, and you can have tens of projects per year. The other different types of data, such as well data, are less volume of data for individual projects, but then you have larger number of projects or wells in this case. So for instance, the last one, if you see the production data, which is the data which comes from pumps and pipelines and networks, is essentially could be 5 megabytes per day per well, but then you can have tens of thousands of well. And so it's kind of interesting, the spectrum of the volume of data that we have, which also makes some of the problems that we work upon challenging. So in a nutshell, what seismic exploration, right? So I'm going to talk about some of the high performance computing and visualization work that we are doing in the Google Cloud using GPUs, especially in the context of seismic processing. So to understand that a little bit, in a nutshell, it consists of two phases, right? So first is the data acquisition. So basically, we have, let's say, boats and vessels which can go out in the ocean, and they can do the seismic surveys. And what basically it's doing is it's sending out seismic waves or sound waves and collecting the reflection data. And so that becomes the data that is, say, for instance, one job's input could be 20 to 100 terabyte of data. So once we have that data collected, the next step is to process that data. Right? That's where really the high performance computing comes into picture. That processing of data is needed to build the understanding or the model of the subsurface, how it looks like. Does it have? Yeah. So like this is, for instance, the subsurface model, which is generated as a result of the subsurface processing. And these jobs are computationally and IO intensive. We have large number of jobs which run in parallel. One small job can take several days, could be 100 kilo core hours. And if I talk about large jobs, it can use thousands of nodes for 1 to 2 weeks, so 3 to 5 million core hours. So we're talking at that scale. So this talk, I'll talk about primarily two things. One is the simulation, that is the HPC processing side, and then I'll talk about the visualization. And both of them we are doing in Google Cloud, and they use GPUs. So for simulation, as I said, the seismic processing that we have, traditionally we have been doing it in-house in our supercomputers, that data centers that we have around the world. And so this journey with Google Cloud started around 5 years back, where we thought that from a business perspective and from a cost efficiency perspective, it will be interesting and competitively advantageous for us to run in the cloud. And that's where this journey started, right? And so today we actually run this in the production in the Google Cloud. And the reason why we chose cloud is basically it would enable us to scale better in terms of dynamic demand, right? So we can, the main advantage that we get is elasticity. So when we have jobs, we can create the infrastructure on demand instead of having a peak capacity planning. Also, we have large volume of resources, the global presence, like I talk about in terms of the data centers all around the world. GPU nodes are critical for us because our software has been using GPUs, and we love GPUs because of the performance per dollar advantage that we get for these types of workloads. Time to decision is a competitive advantage, and we also want to explore different number of scenarios here, so where we can run different types of jobs in parallel. Okay, so to give some background on our Seismic software stack that we have, it essentially has these capabilities of fault tolerance and dynamic resource management, which are critical. And that those are some of the reasons that we have not been using MPI. We have our own software sort of MapReduce like infrastructure and our own scheduler, which is custom. And as I mentioned, we have data centers around the world which are commodity x86 clusters. For some of the jobs, we do use InfiniBand or some high performance kind of networking, especially for imaging kind of applications. GPUs, as I mentioned, are definitely critical elements of our computational infrastructure. So we have had this relationship with NVIDIA even before we were running in the cloud, because we have been using GPUs for 10 plus years. So on the Google Cloud platform, right? So as I mentioned, GPU provide great performance per dollar. We use nodes with up to 8 GPUs. So as Wyatt mentioned, there is a range from 1 to 8 GPUs per node. We use 8 GPUs in most cases to minimize the inter-node communication for processing. For computations, we use, of course, dynamically created VMs. And the VMs, another aspect that we get from running in the cloud is that we can right size our VMs. So we have these different types of VMs in the cloud. And we get that flexibility which is not there in-house. In-house, when we have servers, they are fixed sort of CPU and memory that we have there. So in the cloud, that dimension comes into picture, which also introduces like a level of complexity for us, other than, of course, the advantage, right? So for file system, we use persistent disk for Scratch, Gluster on GCE and GCS as well. We do use monitoring and control since this has been running in production. Some of the internal tools are being used, and also the stack driver monitoring system that Google Cloud has. We use PubSub for some of the control messaging. One of the key element that I want to talk about is the cloud sort of interconnect, right? That is there with respect to the high-speed link that we have for data transfer before jobs. So one of the things that you can see, like by running in the cloud, say these seismic processing, huge computation, you get the great performance, right? But if the data that we're talking about is terabytes and petabytes of data, you need to get that data in the first place from our data centers to the cloud. And if that process itself is going to take days or weeks, then it kind of defeats the purpose. So we actually, with the help of, basically with the collaboration with Google Cloud, we have a dedicated high-speed interconnect between our data center in Houston and the cloud. And of course, security is fundamental to all this aspect. So to give you a little bit more details in terms of the infrastructure and the architecture, how it looks like. So we have here primarily 3 different layers. So the first layer on the top is the durable infrastructure. So these are VMs, right? So we have around, let's say, 6 to 7 VMs. These VMs are running all the time. So for instance, things like our cluster manager, our own sort of internal scheduler. We can have VMs which are doing monitoring, acting as like a centralized logging point or monitoring point. those things are durable infrastructure. Then there's another layer, which is the file system layer, which is existing. But the majority of the infrastructure is here in the middle tier, which is dynamic, ephemeral. So these are the actual compute nodes, VMs, which are a mix of CPU and GPUs, which are dynamic, which do not exist if there are no jobs. And as the demand rises, these VMs are spawned dynamically. We use some of the other capabilities in the cloud, such as PubSub and data flow. And as I mentioned, the data center link that we have is one of the critical aspects that enables us to run this entire workflow in production. So to give you some of the results that we get. So for instance, this graph on the left here shows a seismic imaging job, which runs for several days. So here y-axis is the number of GPU dies here, and x-axis is the time. So you see initially we start to get more and more GPUs, we kind of plateau, and then this job requires additional GPUs, or some GPUs gets free, and then we add more GPUs. So at the peak, we have here around 7,000 GPUs that we are using for this single job, and there are other jobs which are running in addition to this. And this translates to 2 million plus CPU core hours on a single job with 220 gigabits per second on I/O. So on the right-hand side, this graph here is showing the resource count. So these are number of VMs, which could be a mix of CPUs and GPUs. And the x-axis is time here as well. So what the different colors, what it means is the green is the busy, the red is some of the failed nodes, and then the yellow is idle nodes. So these nodes are idle not because we don't have work for them, it's because we keep them idle just for instance, for logging or for figuring out troubleshooting purposes and so on. So what you can notice is, for instance, if you are going to run this in your house, in-house data center, then you would want to kind of provision for, let's say, for the peak capacity here, right? So 5,000 nodes. And then at that point of time, and this is the real sort of demand, so then all this white would be your wasted capacity, or basically you're paying for it, but you're not using, right? But in the cloud, as you can see, all the green is the busy one, so we don't really have any sort of waste capacity here. We are essentially scaling as needed from say, for instance, from 50 to 5,000 nodes. We are able to scale within a matter of 1 hour in this case. Okay. So as I said, this has been running in production, and this picture is actually one of the output of one of these jobs. So this is data from 21,600 kilometer Gulf of Mexico. And so essentially, as I mentioned, for the high performance computing processing, seismic processing within the Google Cloud, the dynamic and the elasticity is really providing us the cost benefits here. So now moving on to visualization, right? So once we are done with the processing of data, we create this Earth's model. The next step is for somebody, for geophysicists or for the people with the domain knowledge, to look at the data, to visualize the data and understand how the Earth structure look like. So then they can see based on the 3D view, essentially, this is where they see the faults or the traps or the possibility of a reservoir, right? So that's the next step. And that's where visualization comes into picture, where you want to visualize these things. So traditional way of visualization for us has been to use our in-house infrastructure, right? And then we have our desktop visualization suites, where the problem is that you have to move all the data from the time you collected the data and the process the data to the place where you can visualize it. And so that movement of data can take days or even weeks in some cases. That's the main problem, right? So to give you an analogy, for instance, Nowadays, we all use Netflix or some sort of other sort of streaming service for watching movies. But before Netflix or other streaming things were there, if you were to watch a movie, you go to a store, you buy a DVD, you bring it to your home, you put it in your DVD player, and so on. So similarly, the same sort of workflow mostly exists in the oil and gas industry for visualization of these oil field data. And because of that data movement, which is an unproductive activity, you also need to plan your collaboration and exploration. You need to make sure that all the your researchers and the great scientists are there available. You need to plan their schedule and so on. So what we have been doing with developing cloud native remote visualization. So essentially the visualization and all the heavy processing, the rendering happens in the cloud on the GPUs running in the cloud. And you only stream the images to your browser. So you can have a browser which could be a thin client, which could be a tablet or a laptop. It doesn't need to have a GPU, right, or any other fast CPU. It can be a thin client, and then it can just connect to the service which will do the actual rendering. So another key thing is basically here is that on the server side, in the cloud side, then these VMs could be dynamic. These could be ephemeral. Based on when the demand is, these VMs could be spawned. And we can have proactively keep a pool of VMs which can make sure that you are getting the fast response rate, but still not wasting the capacity. We store data in the Google Cloud Storage bucket. So as soon as, for instance, you have a data processed from a seismic job, you can upload those models in the cloud storage bucket. So everything is basically in this sort of a data lake environment. And then the visualization service can access the data from there. This is spontaneous. User can sit anywhere and with a variety of more or less powerful devices. So to give you a demo here in terms of how it looks like. Okay. So this picture here, for instance, it's on a world map where you see all these red triangles and squares. So these are your oil field. Let me pause here for a moment. So these rectangles and triangles, these are your seismic surveys here. So these are where actually these surveys were done. So this is showing NPD, which is a Norwegian public data. So this is of the coast of Norwegian Sea here. And basically all these are seismic different types of data sets with different sizes. But roughly, for instance, these sizes range from few hundred gigabits and hundreds of gigabits in general, gigabytes. So then what I can do through this application is basically to look at all these surveys on the world map. So you get a catalog, and then from there on you can click on it, and basically it will start connecting to the visualization service which is running in the cloud. And here you see the data has actually loaded instantaneously. And even though this is a video, I promise I didn't modify the timing or anything in this case. So this was basically that data kind of loads instantaneously in this case. Now in this case, we did have a VM which existed already in the cloud with a GPU. So we can have proactively some VMs which are running, but then it connects to that VM and gets the data from the cloud storage on demand, right? That's what is happening here. And so I can also play with it more, basically move things around here. The data gets loaded on demand as and when it's fetching the data as I'm interacting with the thing here. And there are other controls that we can play with here. So I'm enabling Z slice here in this case. So this is, again, this picture is a 3D view of a seismic model. So this is like an Earth model for the non-domain people here. And then I can also do here things like basically view a slice of 3D slice. So this is volume rendering. Let's just give a minute here. Yeah, so you can see here that it's kind of loading. So to give you a quick picture of what is happening behind the scenes, right? So I was talking you like in high-level application here, which is the front-end application, which you connect to from a web browser. Then you have a bunch of front-end services, and you need sort of a resource manager which can keep track of these VMs, spawn them dynamically as needed, and so on. The main resource is the GPU-based VM here. And you can have like a set of VMs here. You can scale up and down, scale out these VMs. And then the data is stored in the Google Cloud Storage. We do need some sort of data distribution services which can do high-performance I/O, basically high-performance read in this case from the Google Cloud Storage, get the data to the VM, and then the images are streamed back here. So a couple of points before, I think, in terms of the lessons learned and the challenges that we face. So when we initially started this, we started the VM in the cloud. We connected to the browser. It would take, from the first time you click, it would take like 20 minutes to load the first, before you see anything. Right? So it was not that it kind of works instantaneously. There were definitely technical challenges that we faced. So a couple of things that helped us in the process. One was basically doing this level of detail-based visualization. So you see the lowest resolution first, and as you get more and more data, you switch to high resolution data. The other thing is in terms of loading the data from the cloud, we had to really optimize on bandwidth rather than latency. So even though the latency of a particular message request was high, we could optimize by having multiple threads and doing multiple reads in parallel to optimize for bandwidth. So another thing, so this was, as I mentioned, it does visualization by using level of details. So we are not really getting the highest or the full resolution in that case. And that's because we are using one GPU, and so we are limited by the amount of memory the GPU has, as well as the entire architecture is kind of designed around that. Now there are other possibilities that are enabled by these newer technologies, such as NVIDIA Index, and also the fact that Google Cloud is providing us the capability to really, without having to establish our own in-house infrastructure for all the GPUs and all the infrastructure, just to rent out and experiment with these kind of capabilities. So one of the things that we are investigating and have done some work is to use NVIDIA Index. And there's another talk, I think, running in parallel about the NVIDIA Index technology, which is basically, it's a distributed rendering that you can use multiple GPUs and do full resolution visualization with multiple GPUs in the cloud. So we can essentially, the main thing is that data set is kept in memory across the cluster. So here, for instance, I'm showing 2 VMs. Each of them has this sort of data set, 8 V100 GPUs in this case. And one of them acts as index server, one of them as a cluster. You can have multiple cluster nodes based on the size of the data sets. And then you connect from your browser to the thing. It's proven to scale to petabytes. NVIDIA has great demos, I think, in their booth, as well as in some of the talks. And everything, this is basically running in the Google Cloud environment. Okay, so in a nutshell, what Schlumberger has been doing, right, with respect to GPUs in the cloud, we have been using CPUs and GPUs for massive scale seismic processing in GCP. We have been doing this in production for our seismic processing from last 2 years or more. We are also able to create and see newer workflows with cloud GPU native remote visualization workflows, which were not possible in oil and gas industry priorly because we are doing desktop sort of visualization. With cloud native visualization and the new capabilities like full resolution visualization, it opens up new workflows that can be seen. And in summary, we are able to lead innovation in oil and gas high performance computing thanks to the rapid advancement in GPU and the various sort of architectural technologies, and quick adoption of those in cloud environments, specifically in this case, Google Cloud. So thanks for this collaboration and partnership to Google Cloud and NVIDIA. We are able to lead the innovation for oil and gas industry. And that kind of brings us to the end of the talk, and we'll be happy to take questions here.
Thank you. If there are any questions.